Okay, so this is Engineering 245, Lecture 3. This is Part 2 of Lecture 3. I inadvertently closed out that first file. So in this file, I'm going to start off by going over some examples of Newton's second law. And we're going to look at a problem each for the Cartesian coordinate system, normal transverse, normal tangential, and radial transverse. So let's start off with the Cartesian coordinate system. Okay, this is problem 12.28 in the 9th edition of the textbook, and this is the solution that I've posted up. So let's quickly go over this problem. So here we have three blocks that are connected together by a rope, right? And then there are some pulleys. The problem gives us coefficient of friction, the masses of each block, and then we are asked to find the tension in the cord and the accelerations of the three blocks. So anytime you see a problem like this, blocks that are connected together, you should probably, or at least I hope you immediately see that this is similar to the dependent motion problems that we saw way back in the first lecture. Okay? And if you recognize this as one of those types of systems, then you know you could go ahead and relate the accelerations of these three blocks. And that's going to end up being very important to us because what you're going to find if you apply Newton's second law to these three blocks is that you're going to be short one equation. And the way you're going to get that extra equation in order to solve all your unknowns is to make use of this relative motion or this dependent motion type equation. Okay, so going over the process that we use to relate the three accelerations, what you can see is that you could simply let A and C hang down rather than sit on those horizontal surfaces. That just makes it a little easier to see. Right? It makes it similar to the problems that we looked at from chapter 11. So if you go ahead and do that and then go through that process, if you recall, making sure you make use of all the segments and then writing the equation in such a way that you add up to the length of the string, then you're going to end up with this equation for the accelerations, okay, as shown on the bottom here. So that's the acceleration of A plus twice the acceleration of B plus the acceleration of C is equal to 0. Okay, so set that aside. And now you could jump into the second law portion of the problem. So anytime you identify a problem as a second law problem, right? And it should be fairly simple to identify such problems because you're given things like forces or you're asked to find things like forces, and then there are also accelerations involved. Right? So when you see a problem like this, what you see are basically three moving objects. Anytime you have three objects that are going to move kind of in their own way, I know they're related somehow, but you know, each one is going to move in its own way, in its own direction, and so on and so forth. Then you could treat each object separately, meaning each object has its own Newton's second law. Right? So this is actually three separate analyses that you're going to be doing. So take this one block at a time. Right? You can start with A or B or C, it doesn't matter. Take them one at a time. And here is how the book suggests that you work out this problem. And this is a good suggestion. I would also say that you should use this method anytime you solve a second law problem. Right? And the suggestion is this. Go ahead and draw two figures for each block. Okay? And those figures are going to represent the second law in graphical form. So what I mean by that is if you look at the left-hand side of the second law, it says sum of forces. So what you want to do is you want to draw a figure that has all the forces acting on your object. You might recall from statics that we call this a free body diagram. All right, so draw the free body diagram for each block. And the other figure you're going to draw is essentially the right-hand side of Newton's second law, which means mass times their accelerations. Right? So think about what kind of resulting motion you're going to have, and then draw the figure to represent that. And the reason you want to draw these two figures is it's fairly simple to draw these two figures, and once you've drawn them, it makes it much easier to convert them to the numerical form, if you will, or the equation form of Newton's second law. So let's see what this looks like for block A. All right? And I'll talk a little bit about this whole idea with static equilibrium in a few seconds. Okay, but first of all, look at the free body diagram. All right, this is going to be a review of statics. So you look at that figure and you say, okay, what are the forces acting on block A? Right, it's going to be the weight, of course. There's a normal force since it's sitting on the surface. Right, that normal force, if you remember, always acts perpendicular to the surface. And then since a coefficient of friction is given, you put in that friction force. Okay? And then since there's a cable attached, you know there's a tension in the cable. And remember from statics again, tensions always pull away from the body. All right, so there's your free body diagram. Now, why do we draw this using the coefficient of static friction? So the book says, right, that anytime you have a problem dealing with sliding objects, like these sliding blocks, and there's friction involved, then you need to make sure that there's actually going to be motion. Do we agree that the friction might be so large that these objects don't even move, right? Meaning these objects are in static equilibrium? You should agree with that statement, right? So the way we're supposed to make sure that this problem actually is a dynamics problem is to go ahead and first solve it as a static problem to see if the static equilibrium is exceeded. Right? Once the maximum frictional force has been exceeded, then we know that the objects will move and we will have a dynamics problem. Right? So practically, let me say this. Since this is a dynamics course, I could guarantee you that every single one of these problems you encounter will end up telling you that you do have dynamics, that you do have motion, right? But it's a good idea to kind of go through the formality. All right, the book kind of suggests it, and out in the real world, you would go through this formality. On an exam, you don't have to worry too much about that. Okay, I will obviously give you problems where you do have motion. Okay, so you don't have to check formally to make sure that there's no static equilibrium. But, right, since we are required by the book to do so, let's kind of talk a little bit about how we check to make sure that there's motion. All right, so you first treat this as a static equilibrium problem, and what you're going to say is that if this is static equilibrium, right, then nothing is moving, which means if you go up to this figure, A, B, and C are all staying still. And if that's the case, then if you look at B, right, B's got a mass of 10 kilograms, which means it's got a weight of 10 times 9.81, right, in newtons. And that's just the force on B that's pulling down. And then you've got 2 lengths of the cable that's pulling up on B, which means each tension, right, is half the weight of B. So if you go down here, right, in order for me to have static equilibrium, you know that the tension acting on block A is half the weight of B, which works out to be about 49 newtons. Okay, and then the frictional force we know has to be equal to the coefficient of static friction, that's 0.24, right, times the normal force. The normal force simply cancels out the weight, right? So if you look at that, if you calculate that frictional force, it's 11.8 newtons, whereas the tension is 49 newtons. Okay, so the tension is much greater than the weight, which means, of course, block A will move under that tension. That tension is going to pull block A towards the right. Okay, so that's how you check to make sure that A will indeed move. Then you do the same thing for B and C, right? So we do C, right? We do it essentially the exact same thing. We're going to find that C moves, right? And once you know that A and C are going to move, do you need to check whether B moves? Of course not, right? A and C only move because B is pulling them down. So you don't need to check B, but now you could go to the dynamics part of the problem. Okay, so here are the two diagrams now for block A. We have essentially the same forces, right? Weight, tension, normal force, and the frictional force. But the frictional force now, we're going to make use of the coefficient of kinetic friction. And then if you look at A, we know that the only acceleration that's going to happen is it's going to move towards the right. So there's that, mass times A times acceleration of A, all going towards the right. All right. So we obviously do not need sum of forces y equal to 0 for this block. I mean, you could write it out if you want, but what is that going to give you? All that's going to give you is that your normal force is equal to the weight, right, which is 49 newtons again. All right, so all that leaves us with is sum of forces x equals to mass times acceleration of A, right, all in the x direction. So that's tension minus the frictional force is equal to 5 kilograms times acceleration of A. Notice that I have two unknowns here, tension and acceleration of A. Okay, then we're going to go to block C. It's very similar to block A, it's just that block C has a different mass or a different weight than block A. So I get a very similar equation. All right. Obviously, the signs are different because C moves in the opposite direction from A. All right, so, but I get a very similar equation. Two unknowns here, tension and acceleration of B. Then I move on to block B. All right, there's two tensions. Right, I put that as T2. There's actually not too much of a need. What you can do here. Okay, if you see this, you could immediately put this as 2 times T, right? Because there's two lengths of the string on both sides of that pulley, right? So that's twice the tension that's pulling up on block B. Okay, so I've got 2T pulling up, I've got weight of B pulling down, and all of that has to be equal to mass times acceleration of B, which goes downwards. Okay, so the only equation that's relevant here is sum of forces y is equal to mass times acceleration in the y direction, right? And if I write that out, I get two more unknowns here, T, tension, and acceleration of B. So if you look at your three equations, right, one each for blocks A, B, and C, you notice that there are four unknowns. I've got tension as an unknown, and then the three accelerations. Acceleration of A, acceleration of B, acceleration of C. And how many equations? Well, we just said, right? If you just use the second law equations, that's three equations to solve for four unknowns. Which is why, way back in the beginning, we needed that equation that related the three accelerations. Because now, along with that, we would have four equations with four unknowns. Okay? And that's how you're supposed to solve this problem. This is a problem dealing with four equations, four unknowns. And you'll notice, right, the way things are written out here, we've already gone ahead and applied that acceleration equation. Notice that acceleration of A is written in terms of accelerations of B and C. And if I do that, now this is three unknowns. Okay? So you could go ahead and solve these three equations however you want. You could use a calculator if your calculator could solve systems of equations. And these are the three accelerations that you get. All right, so that is an example dealing with Cartesian coordinates. Keep in mind then, right, always draw your two figures. And once you've drawn your two figures, then it's very easy to go ahead and write out your equations. So let's look at an example dealing with normal tangential coordinates. All right, so let's move on. I believe that's this one that I wanted to look at. Yeah, okay. So in this problem, we've got a car, a 2,400 pound car, that's traveling over the top of a hill, right? And that hill has a radius of curvature. And we know that if A is moving at 100 miles an hour on the top of that hill, then it just loses contact with the road, meaning it's about to fly off that road, okay? What we want to find is the radius of curvature, right, at that point on top of the hill. And then we want to find the force exerted on a 160 pound driver by the seat if the car is now a different weight, all right, 3,100 pounds, and if it's traveling at a constant speed of 50 miles an hour. So the first and the second parts of this problem are completely unrelated, meaning in the first part of the problem, we've got a light car and it's moving fast enough to lose contact with the road. In the second part of the problem, we've got a heavier car and it's not moving anywhere near fast enough to lose contact with the road. Okay, so let's start with the first part. If the car is going to lose contact with the road, then, well, if there's no contact, then there's no normal force, right? It's almost like the car is now flying through the air. So there's no normal force, which means the only force acting on this car at that point is your weight, okay? So look at your two figures, very simple figures, right? In your free body diagram on the left, you just show the car with the one force acting on it, that's the weight of 2,400 pounds, okay? And then on the right-hand side, okay, if there are no forces in the x direction, in the horizontal direction, then there obviously isn't going to be any acceleration in that direction. So all you have is an acceleration going downwards. And since this is going around a curve, you know that that vertical distance is actually your normal direction, right? Remember, normal direction points towards the center of curvature. So with this, you could go ahead and write out your second law equation. I wrote it as sum of forces y. That should have been written as sum of forces normal. Okay, you want to stay consistent. Okay. Meaning this term here, I should have put in sum of forces normal is equal to mass times acceleration normal. Okay, and in order to work out this problem, we have to convert our velocity, okay, in miles per hour into feet per second. So make sure you know the conversion, right? 5,280 feet per mile, an hour is 3,600 seconds. All right, so now if you look here in your second law equation, okay, so you notice I just said earlier that I really should have made this everything in terms of normal. Well, positive normal is towards the center of curvature, okay? So if I were to convert this all to normal, then the negative signs would just disappear, okay? Both negative signs here would disappear because both the force and the acceleration are actually in the positive normal direction, okay? But anyway, that's not important, right? What happens is if you go ahead and look at your acceleration normal, you know when you use the normal tangential coordinate system that you have to make use of this definition for acceleration normal, right? Acceleration is equal to velocity squared divided by the radius of curvature. And if you look at that, then obviously the only unknown here is going to be your radius of curvature. So if you solve for it, you get 668 feet. Okay? How about the second part of this problem? You've got a 160-pound driver, right? And you've got this car that's now moving at a constant speed of 50 miles per hour. So how do we work this out? Well, before you even try and write your equations, keep in mind, just draw your two diagrams. All right, so now we basically look at the driver, right? What are the forces acting on the driver? So on the left-hand side, you can see you've got this you've got the weight, okay, 160 pounds, and then there's a normal force because the driver now sits on the seat. So there's a normal force exerted by the seat on the driver. And then, right, if we want to know the force, right, we know that's related to the acceleration, and the resulting acceleration is, again, just in the normal direction, right? You look at this figure, your free body diagram, and again, there are no forces in the tangential or the horizontal direction, so all your forces are in the normal direction, okay? And again, convert your velocity to feet per second. You're going to apply sum of forces, normal is mass times acceleration, normal again, right? And here, again, I had done this using the y coordinates when I should have used normal. So what you want to do is you want to reverse the signs here. This should be weight minus normal is equal to positive mass times velocity squared over rho. And now that we know the radius of curvature, right, we're going to plug that in, and the unknown here now is going to be the normal force, which of course is the force that the seat exerts on the person. All right, so that turns out to be 120 pounds. What you're going to notice is that normal tangential coordinate system problems are usually actually going to be fairly simple because you know the only thing that you have available to you to make use of is sum of forces equals acceleration, where acceleration normal is going to be your velocity squared divided by radius of curvature. Okay, so there's always going to be a velocity involved whenever you're using the normal tangential coordinate system. All right, so finally, we're going to look at an example of radial transverse. So let me see if I can find the correct problem here. Okay, so 12.68 out of the 9th edition. Okay, is very similar to the types of problems that we discussed last time, meaning there's a rod that's driven by a motor. Okay, and there's a collar on this rod that just slides back and forth. And what we have are the two equations that define how r and how theta change with respect to time. Okay, so that's all given to us right here. We want to find the radial and the transverse components of the force exerted on the collar when time t is equal to 1 second and when time t is equal to 6 seconds. Okay, so just for your own information, if you will, what exactly do the radial and transverse components of the force look like, right, on this collar? Well, the transverse component is fairly simple. That is the arm pushing on the collar, right? That arm pushes on the collar to get that collar to spin along with the arm. So that's the force that we're talking about, right? The radial component is a little trickier, but it's not too bad, right? That is basically the linear acceleration. When you drive a car, when you accelerate a car in a straight line, right, you feel yourself being forced back into the seat. Right? There's a force exerted, right? And so that's similar to this force, this radial force on the collar. If that collar accelerates along that arm, then there's a force that's being felt by that collar, right, in that radial direction. So these are the two accelerations that we're looking for. Okay, so you know this is a second law problem since we're looking for forces, and you're going to apply sum of forces in the radial direction is mass times acceleration radial, sum of forces transverse is mass times acceleration transverse, where your accelerations, right, are given by these two equations here that you remember from last time, right? The ones that deal with the first and the second derivatives of r and theta. So what you're going to need, okay, is you're going to need to differentiate r and theta. And basically you're going to differentiate these two equations, right? And then you need to plug in your values at 1 second and 6 seconds. All right, so you start with R. We need R at 1 second and 6 seconds, so you just plug in your values. That gives you 2 feet and 1 foot, respectively. Then you're going to take the first derivative, right? That gives you -10 over the quantity t plus 4 squared. Work that out for 1 and 6 seconds, okay? Then you do R double dot, right? The second derivative, do the same thing. Then you go on to theta, right? Take the first derivative, take the second derivative, and find your quantities at 1 second and 6 seconds. And now you could find your accelerations, right? What you're going to do is you're going to find your accelerations for R and theta at 1 second and 6 seconds. And once you have that, then you just apply sum of forces is mass times acceleration, where now your forces are the unknowns, right? Your mass is 5 pounds divided by 32.2 feet per second squared. Remember, this is a US unit problem, so you're usually given weight, not mass, right? So if you're given weight in pounds, you've got to divide by acceleration due to gravity to convert it to mass in slugs. Okay, so go ahead and do that, and you can see this is how you come up with forces, okay, for both 1 second and 6 seconds. All right, so I hope what you see from these 3 examples is that these types of problems are actually fairly simple, okay? In this one thing I did leave out in this solution is I forgot to draw the figures for this problem. This problem is simple enough that there's actually no need to draw the figures, right? But if you were to go ahead and draw the figures, right, this is what you would draw. I draw my color, right, and I'm going to draw all the forces acting on it. I know there's going to be a radial force. Okay, so this is force radial. I know there's going to be a transverse force, force transverse. And then I know there's going to be a radial acceleration. And a transverse acceleration. So it's very trivial for this problem, which is why actually those figures weren't even shown here. All right, but it's still a good idea to kind of draw both figures. Right? You want to get used to using this process, right? And always drawing your figures. Okay, so those are our examples, and let's go on and continue with the rest of this lecture. Okay, so the next thing we want to talk about is something called a linear momentum. You've all probably seen this before in physics, right? Linear momentum is derived from Newton's second law, okay? And here's how it's done. So we start with F equals ma, and then what we replace this acceleration with, right, is by its definition. It's mass times dv dt, right? And that's mass times v dot, just to write it in a simpler form. And since mass is constant, what you can look at this as is force is the first time derivative of this quantity, mass times velocity. And we're going to give that a name. mv, right, is what we call linear momentum. And we use the symbol capital L in this textbook. I know you probably use different symbols in physics, but unfortunately there's no standard convention when it comes to these to this notation. Okay, so anyway, we can now rewrite Newton's second law. If you look at this, okay, this is the first derivative of linear momentum. So now Newton's second law can be written as sum of forces is equal to L dot, the derivative of linear momentum. Okay? So that's just an alternative way of looking at the second law. Linear momentum, okay, is, if you think about it, it's mass times velocity. So what it really represents is a tendency for an object to just keep moving in the direction that it's got a velocity in. Okay? So what I mean by that is this. If I have two objects that have the same velocity, but one has a lot larger mass than the second, then the one with the larger mass has a larger momentum. How much harder do you think it is to stop that object with the larger linear momentum? It's obviously going to take a lot more for you to stop that object that has a larger mass, right? On the flip side, right, if both objects were at rest, right, how much harder is it to get the one with the larger mass to move, to kind of start moving at the same speed as the one with the smaller mass, right? It's going to be much harder. So linear momentum by itself is just kind of it's a measure, if you will, right, of the tendency for an object to just keep moving in the direction it's moving in, or it's a measure of how difficult it is, right, to stop that object once it's moving at that velocity. Okay, so that's linear momentum, and we're not going to do too much with this yet. Right? We will use this a little more in later chapters. Okay, so it's just a definition that we're going to come up with. It's another way of looking at the second law. The second definition that we want to define, okay, it's also also just a definition. Okay, before we get into that, just quickly, the units that we use for momentum, it's a mass times a velocity, right? So it's a kilogram meter per second, or it's a slug feet per second. Okay. Anyway, right, this is just a brief summary of all the units that we're going to be using, okay, when it comes to the second law. All right, so this second definition that I wanted to get into, okay, is something that we call an angular momentum. Angular momentum, okay, is a purely mathematical definition. What that means is someone just came up with this definition for it, and it doesn't have to have any physical meaning. It's just a mathematical calculation, right? And the definition that we use is this. It is the cross product of a position vector with the linear momentum vector. And you might recall, right, that when you take a cross product, right, that has to do with the position vector, then you have to take that cross product about some point. Okay, so we're going to call the point that we're taking the cross product about point O, right? And we're going to use capital H to designate angular momentum. So this is, again, a purely mathematical definition. This says, if I have an object, okay, let me bring up my pen. If I've got an object that's moving, that's got some mass and it's moving with some velocity, then it's got a linear momentum, mv. Right, L equals mv. And what I can do is I could pick some point O, right? And now that object at this particular instant is going to have a position vector from point O. So there's R. I could define H about point O as R cross with MV. So this is a completely random definition, if you will, right? Someone just came up with it. Now, there's a reason that they came up with it, right? Because it actually does describe certain physical phenomenon. But as far as mathematics goes, this could be purely random. I could come up with my own definition, right? I could come up with some definition, I'm doing this like just off the cuff here. I could come up with J about O is equal to R cross acceleration. I mean, I could do something like that, right? And I just call that, I could name that whatever I want. Well, someone did exactly that for angular momentum, okay? So this really doesn't have any meaning, because if you think about this, right, I could pick this point O, and I could have this object, right, that's moving, and maybe a few seconds later, it's now here. My object is now here, and it's got some mass times velocity, some new mass times velocity. So now my r vector is here, right? And I could do a new cross product between r and mv. And that's going to give me something completely different from that first value. So, I mean, what does that really mean? It doesn't mean very much, right? And then that object later on might move down to here, right? And now it's got some new mass times velocity, and now I have a new r vector, and I could take that cross product again. So, doesn't really mean anything, all right? It's something that could keep changing. So, when is this going to have meaning? Okay. Well, if you think back to another very important case where we made use of a cross product, okay, it was in statics when you took the moment of a force about some point. And a moment of a force about some point is very similar to this in that it's a purely mathematical definition. Okay, I could have a force, let's say 100 pounds, acting in that direction at some point, and then I could take the moment of that force about this point O, right? And the way it's defined, if you remember, is very similar. I say moment about O is R cross F. Doesn't have to have any meaning. I could take the moment of any force about any point, right? It could be something completely random. I could take the moment of the weight of a person about the sun, about the center of the sun. Can I go ahead and take that cross product? Yes. Am I going to get some kind of mathematical quantity? Sure, right? I get some huge value, but what does that really mean? It means absolutely nothing, right? It's got no physical meaning. So when does moment of a force about some point actually have a physical meaning? Well, it's when you start applying physical objects, right, like a wrench. If this were actually a wrench and I was pushing on the end of that wrench, now what does that moment represent? That moment represents the amount of twist, the twisting force I'm applying to this point O. Okay, so when there's a physical connection, then moment, then that cross product between R and F has a meaning. So I could pretty much say the same thing then for angular momentum, okay? Angular momentum by itself is just a useless or meaningless mathematical definition. Where it actually starts to become important and make physical sense is when there's a connection between that object that I'm looking at that has a linear momentum, right, and that point O. And let me give you the case where it actually has a physical meaning. It's when there's a physical connection between my object and a point O. And for us, okay, this is going to be in the form of what we call a central force problem. A central force problem is any situation where you have an object that's moving, and then there's a force, a single force that's pulling on that object, pulling it towards a fixed point. So when does something like this happen? So here's mv, right? It's got a linear momentum, and then there's a force pulling on it towards a fixed point. Well, this happens in any type of a rotation problem, right? If I take a ball on a string and I swing that ball around, then what is the central force? It's the tension in that string, right? And what does angular momentum now represent? If I do R cross mv, right, not only is that a force, that's also a position vector, right? I'm sorry, position vector is opposite, right? There's R. But if I take this cross product of R cross mv now, and that object is being swung around a fixed point, then the angular momentum represents the tendency for that object to just keep spinning around that point. Okay? The larger the angular momentum, the faster it's spinning around that point, right? The more it wants to just keep spinning around that point. Okay? Because what happens to the angular momentum once I cut the string? Well, once I cut the string, that ball just flies off, right? I've lost my angular momentum. And that ball now has only linear momentum, and it just wants to fly straight off in a straight line in the direction it was moving in. Okay? So angular momentum is only important, or it only has meaning when there's a physical connection. So the ball and the string being swung around is a perfect example, but a probably even more important example is in space mechanics or in any kind of an orbit problem. Okay, so when you have some kind of a satellite that's orbiting around a planet, right? That is a central force problem because you have the satellite that's moving with some velocity, so it's got a linear momentum, and then there's only one force that's acting on it, and it is the pull of gravity. Gravity is always pulling that satellite towards the center of the planet. So that's your central force. And what that central force does is it gives that satellite an angular momentum, right? That satellite now basically has a tendency to want to just keep spinning around the planet. Okay, that is the most important type of central force problem. And again, it's also what we refer to as a space mechanics problem. So it's not just satellites orbiting around planets. It could be any type of a spacecraft orbiting around a planet. It could be a moon orbiting around a planet. It could be a planet orbiting around the sun, right? But it's any type of situation where you have an orbit. So we will talk a little bit more about orbit problems in this lecture, but the rest of the material that deals with orbits is actually in chapter 13. Okay, we're going to define a very critical equation for an orbit problem in chapter 13. So we're only going to introduce orbits briefly in this chapter, in chapter 12. Okay, so let's start talking about orbits. And before we do that, okay, just another quick thing about angular momentum. Angular momentum is defined as this cross product, as now we've discussed for several minutes. You might recall from your calculus or even your vector algebra that the magnitude of this cross product, right, because the cross product results in a vector, and the magnitude of that vector quantity, okay, is the product of the two magnitudes, which means r, the distance, times mass, times the velocity, right, times the angle between your two vectors. So let me illustrate that more clearly. If I've got 0.0 here, right, and then here's my r vector, and here is my object with some linear momentum, okay, h, the magnitude of h, let me put these two bars to indicate magnitude, is equal to rmv, that's the product of the two magnitudes, times sine of the angle between the two vectors. So what that means is I could slide my vectors, draw them tip to tail. This will be the angle phi. Okay? So keep that in mind because we're going to make use of this. All right, we're going to actually make more of magnitudes than we do of the vector quantity when it comes to angular momentum. Okay, so let's continue on with the slides. So when it comes to orbit problems or space mechanics, okay, here is something that, that is very interesting. Okay, you can start off with the definition now for angular momentum and take its first time derivative, which means h dot, right? And there are some rules that apply when you take the derivative of a cross product. It's very similar to the chain rule, right? But the end result is you end up with this. You end up with the first derivative of your angular momentum is r crossed with m times acceleration, mass times acceleration, which is nothing more than your force, right? So the first derivative, okay, of your cross product is r cross f. That's very important, okay, because, okay, if we go back to here and we take a look at an orbit problem. An orbit problem, let's say, is anytime you have, right, so I've got some satellite that's orbiting about the Earth. Let me call it Earth E, right? Here's my satellite. So this satellite has a velocity that's tangent, right, to this circular path. So this is mv. We know r is here, right? R is the position vector from the center of the Earth to that satellite. And then the force, the central force, is there. It's just opposite in direction to r because gravity is pulling towards the center of the Earth. Okay, so there's F. Now, we had just said that first derivative of angular momentum is r cross F. Well, what are r and F? If you look at this figure, they are in equal and they're in opposite directions, right? Or they're parallel to each other. What is the cross product of two vectors that are parallel to each other? It's 0. Okay, so if this says in any orbit problem, the first derivative, the first time derivative of your angular momentum is 0. Well, if h dot is 0, what does that mean as far as h is concerned? H is a constant. Okay? This is a very, very important fact of any orbit problem. It's the angular momentum in any orbit is a constant quantity. Okay? So r cross mv is constant, okay, in any orbit problem. And that is one of the most important principles, okay, when it comes to these orbit problems. Okay? And that is actually the hallmark feature, right? It's the most important feature of angular momentum in orbits. Okay? So we're going to take a look more now at these orbit problems. Okay? So this is what we just talked about, right? H must be constant in any orbit problem or in any central force problem. Okay? And what that means is in scalar form, if I pick any two locations in an orbit, right, I have some orbit, I have an orbit, and I pick any 2 points along that orbit, right, maybe here's the Earth, then RMV sine theta here has to be equal to RMV sine of the angle here. Okay? It's constant. I can pick any point actually on this orbit, and its angular momentum has to be equal to these quantities. Now, I am pretty certain that some people at this point are saying, well, this seems like a very trivial idea, right? And the people who are thinking that are probably the ones who assume that every single orbit is circular. If an orbit is circular, then I've got perfect symmetry, right? And it should be fairly intuitive that the velocity at any point on the circular orbit is going to be constant. So, and then the radius is constant, of course, right, at any point on this orbit. So, R cross mv, or RMV sine of the angle, obviously it's going to be constant, okay, no matter what, in the circular orbit, okay? And that would be, you will be absolutely right, but, okay, the circular orbit is not the only type of orbit that exists. So, we're not going to go into the proof of what I'm about to say. Okay, if you're looking for a proof, you can find it in more detailed physics books. You can look it up in any book basically that deals with space mechanics and orbits. Right? But this all comes about from the work of Newton and Kepler. They were both able to prove mathematically that there are exactly two types of orbits. Okay. There is a circular orbit, which we just discussed, and then there's an elliptical orbit. Okay, meaning your satellite or your planet or your moon traces out an elliptical path. Like so, okay? And here is the critical thing. In an elliptical orbit, okay, the planet, or whatever it is you're orbiting about, is always offset to one side of the major axis, okay? Your orbit, your planet, is never right in the center of that ellipse. Okay, that is physically impossible. Okay, and again, Newton and Kepler have proven that. Okay, so this is the other type of orbit. And now, this idea that angular momentum is constant at any point on this orbit becomes a lot more powerful. Okay. So think about this. I could pick any 2 points on this orbit. Let's say I pick this point. Okay. If you look at this, I've got velocity that's tangent to the curve at that point. All right, so there's mv. But then look at r. R is this quantity. And then what is that angle? This is the angle. There's phi for that point. Okay. Now, what happens if I choose this point? There's mv. Okay. There's r. There's the angle phi. Can you see that the radii, the r's, are completely different? The angles are completely different, right? And yet, when I do r cross mv, that's going to give me the same value at these 2 points. Okay, even though, again, r and that angle phi are completely different at those 2 points. What this is going to tell you, okay, is that your velocity is also different at those 2 points. So in a circular orbit, it's fairly obvious that velocity is constant. But in an elliptical orbit, okay, now we've proven that velocity actually is not constant. Okay, if I am to satisfy this equation that angular momentum must be constant, then velocity must keep changing when you're in an elliptical orbit. That is a very, very important result. Okay, you do not have constant velocity in an elliptical orbit. So we will talk a lot more about elliptical orbits in the next chapter. Okay. For now, let's continue on with the circular orbit. In the circular orbit, okay, things actually become fairly simple. Angular momentum, of course, is constant because it's fairly obvious that velocity is constant and radius are constant. Okay, So all we really need to do is come up with one equation for a circular orbit. We want an equation that basically relates the distance from the center of the planet and the velocity of your object, or the velocity of the satellite, if you will, in our example. So the way we're going to derive that, okay, first is we first need to make use of Newton's law of gravitation. So we all know that Newton came up with 3 laws of motion, right? The first law, second law, third law. But it's important to realize that Newton also came up with a 4th law, right? That's the law of gravitation. And if you remember from physics, all he said in that law was that if you have 2 objects, right, of masses, big M and little m, and there's some distance r from each other, then they're going to attract each other with equal and opposite forces. And the magnitude of that force is equal to some constant g times the product of the 2 masses divided by that distance between them squared. Okay? And g is what he called the universal constant of gravitation. Universal meaning it's constant, right? It's the same anywhere in the universe. And g can be found to have the value shown here, right? On the top is in SI units, on the bottom is in US units. Okay, so it's a very important constant. And we actually use this law of gravitation a lot. Okay? When we calculate the weight of an object, we say weight is equal to mass times acceleration due to gravity, right? Well, that is actually a special form of Newton's law of gravitation. Okay? On the surface of the Earth, right, what is the force referring to? Well, the force is the weight of the object, right? When you have an object that sits on the surface of the Earth, your 2 objects are that object and the Earth. So if we make big M the mass of the Earth, small m the mass of your object, then force, right, is nothing more than the weight of the object. So there's weight, right? And then there's small m, right? That's right here. The rest of this equation, big G times mass of the Earth divided by this r squared, right? It's going to end up being a constant if you think about this. Okay, so big G we know is already a constant. Mass of the Earth obviously is a constant. What is the distance between the Earth and some object that sits on its surface? Well, for anything that sits on the Earth's surface, right, the Earth is going to be much larger. So the distance between the center of the Earth and the center of that object is essentially the radius of the Earth. And what's the radius of the Earth? Well, it can be taken to be another constant. So what is g? What is acceleration due to gravity? It is actually g times mass of the Earth times radius of the Earth squared. Okay? That's where we come up with this acceleration due to gravity. All right, so that's Newton's law of gravitation. And it's a quite an important law because of this idea of weight, right, of something on the surface of the Earth. But we're also going to make use of this now, okay, in a circular orbit. So let's take a closer look at a circular orbit. Okay. I mentioned radius of the Earth, right? So radius of the Earth is a very important quantity that we're going to need quite often because we're going to deal with a lot of orbit problems about the Earth. Okay, so it's a good idea to memorize the radius of the Earth, okay, because you're going to use it so much. And here they are. Okay, it is about 6.37 times 10 to the 6 meters, or 3,960 miles. And of course, you probably will be converting that 3,960 miles to feet. Right? So remember that conversion, 5,280 feet per mile. All right, so now, circular orbits. Okay, so we start with this Newton's law of gravitation. That force, okay, is going to be the force of the Earth pulling on the satellite, right? That is our central force, if you will, okay? And we know that the velocity of that satellite is just some constant value v. And we're going to look at this. Since this is a completely circular path, it will be very easy to use normal tangential coordinates. So my velocity is in the tangential direction, right? And my force is going to be in the normal direction. So that force is just what's given by Newton's law of gravitation, right? But that force is also equal to mass times acceleration in the normal direction, right? Because that force is in the normal direction, it results in an acceleration in the normal direction. And what do we know about acceleration in the normal direction? Well, it's velocity squared divided by the radius. So now you can go ahead and equate, okay, the two equations here. There's the force, right? And this is actually mass times acceleration. This is all in the normal direction. You're going to get a lot of cancellation, right? You're going to get and you're going to get some simplification. And the end result is very important. It's this. The velocity squared of anything that's in a circular orbit is simply given by big G times the mass of that planet, right, of the mass of the Earth in this case, divided by R. R is the distance between that object, that satellite, and the center of the Earth, okay? Or it's equal to acceleration due to gravity on the surface of the Earth times radius of the Earth squared divided by that distance R. Okay? This is a very, very important result. This equation, okay, is all you need for a circular orbit. What this tells you is that if there's a satellite that I want to place in a circular orbit at a certain distance above the Earth, then I cannot choose the velocity of that satellite. Okay? I have to plug in the distance that I want into this equation, and this equation will tell me exactly how fast my satellite has to move. Likewise, if I have a satellite that has a certain velocity and I want to place that into a circular orbit, I cannot choose how far from the Earth I put that satellite. Okay? For that given velocity, there is a prescribed distance. Okay? So it's one or the other. You cannot choose both. Okay? And that's the thing about circular orbit is there's no choice. Okay? If I choose my velocity, then I can't choose my distance. If I choose my distance, I can't choose my velocity. Okay? Now, if you look at this equation again, this is a very, very important result. Okay? Big G, big M is actually equal to small g times radius of the Earth squared. And why do I say this is important? Because in a lot of equations, okay, the equation is derived using big G and big M, right? But big G, as you saw earlier, is a difficult number to memorize, right? And mass of the Earth is also a fairly difficult number to memorize, right? So rather than using those two difficult constants, it's much easier to use small g, which we all know is 9.81 meters per second squared, or 32.2 feet per second squared, right? And then the radius of the Earth, which we knew, okay, or which we showed earlier as being pretty simple. It was 6.37 times 10 to the 6 meters, or 3,960 miles. Okay? So a lot of times it's more preferable to use small g, big R squared, rather than big G times big M. Okay? So, why are they equivalent? Why is big G times big M equal to GR squared? Very simple, right? Remember we said that G, M over r squared is equal to mass times acceleration due to gravity on the surface of the Earth. So on the surface of the Earth, what is small r? It is radius of the Earth squared, right? Then the masses cancel out from both sides, and now you just rearrange and you get gm is equal to g r squared, okay? Very simple result, but it is extremely powerful because this is much easier to use than big G, big M. Okay, so go ahead and use that shortcut. Okay, on an exam, okay, sometimes I get students that come up to me and ask me, well, I don't know what mass of the Earth is. I don't know what the universal gravitational constant is. Can you tell me what those terms are? And I'll usually tell them, no, you don't need those terms. Okay, and the reason is you could just as easily use acceleration due to gravity on the surface of the Earth and radius of the Earth, okay? All right, so that's a circular orbit, okay? And let me talk a little bit about how we place a satellite into orbit then, okay? And it's actually fairly simple once, now that you have these equations. So if you are trying to place a satellite into a particular orbit, okay? So here's the Earth. Here's the orbit you want to place your satellite in. Then usually you've chosen the distance, okay? You've chosen r, right? The distance r. You've chosen r, and that means you've plugged r into that equation, right? V squared is equal to gr squared over r, right? You've plugged it into that equation to find v, right? And so now you know how fast your satellite has to move, right? So the way you would launch that satellite into orbit is you would place it into a rocket, you would shoot that rocket out to the correct radius. It must be exact, okay? You must shoot it out to that exact radius. And then you would release that satellite. That satellite would have its own engines, right? You would fire up those engines, and you must make sure that you fire those engines in such a way that that satellite moves off, shoots off in the direction that's perpendicular to that radial direction. Okay, it must be moving in that tangential direction. It must be exact. This must be 90 degrees. Okay, and this must be moving at the correct velocity. And if you meet those requirements, then your satellite stays in orbit. It goes right into that circular orbit, right, and it will stay in that orbit. Now, obviously, this is all assuming that we have ideal conditions, meaning the Earth is going to be a perfect sphere, right? The gravitational pull is always constant, and so on and so forth. In real life, we know that the Earth is not a perfect sphere, right? So the central force, or the force of that gravitational pull, is not constant. However, okay, this is the starting point for launching the satellite into a circular orbit. And then obviously if you are NASA or any other organization that launches satellites, then you have to make periodic corrections, right, to make sure that that satellite stays in orbit. Okay, but that's obviously an advanced thing, right? Even NASA uses these equations as a starting point for the work that they do. Okay. Another thing that we're going to be looking at when it comes to these orbits then, right? Next time we'll start talking about elliptical orbits. And then in a lot of cases, okay, we move back and forth between orbits. I can move back and forth between circular orbits. I can move back and forth between two elliptical orbits. Or I can move back and forth between a circular and an elliptical orbit. Okay? We call that transferring between orbits. And we will get into the details of that next time. Okay, so this is your very brief introduction to orbit mechanics. As I said, we're going to save the bulk of what we're going to do as far as orbits are concerned for chapter 13, okay, because that will allow us to paint a more complete picture of orbit problems. Okay, so even though I've got some stuff here in my chapter 12 slides dealing with elliptical orbits, we're not going to get into this yet. Okay, we will talk about this in chapter 13. All right, so with that, okay, let me end this lecture. I don't think there's a need to go into examples of circular orbits, right? It's a very simple equation. There's really not much I could show you other than plugging in some numbers, right? So we won't do that. You should be able to do that on your own. Look at some of the sample problems that I've posted up. Look at sample problems in the book, okay? And that should be enough for you to get a good understanding of circular orbits. Okay, so let me end this lecture here. Let me briefly say that this should hopefully be the last video lecture. Okay, our next lecture hopefully will be in person. Okay, so look for an announcement. Regardless, all right, whether the next lecture will be by video or whether we're actually going to start meeting in person, I will make an announcement on Blackboard, so stay tuned for that. All right, so let me end this here, all right, and until next time, make sure you're caught up on this material. This is chapter 12, okay, to remind you. Okay, so let's end this here.